Hello learners, welcome to session 2 of Unit 5 in the course Introduction to Abstract Algebra. I am Unkaila Desmani, your course instructor. In the previous section, we look at definition of complex numbers. In this session, you will learn more about operations on complex numbers such as commutativity, associativity, and then distributivity with respect to complex numbers. So in particular, we are looking at complex arithmetic in this session too. By the end of this session, you should be able to add complex numbers, subtract complex numbers, multiply complex numbers, and also divide complex numbers. Addition and subtraction of complex numbers. Addition and subtraction of complex numbers. To add two complex numbers, we add their real and imaginary components separately and use the distributive rule for the imaginary parts. So let's look at, for instance, so this example 2 explains that rule. Suppose that z equals 3 plus 2i, z2 equals 4 minus 3i, and then you also have z3. You want to find the first one. Take my marker. First one, a, that is z1 plus z2, and that will be equals to z1 is what? 3 plus 2i. You add also z2 4 minus 3i together, and what do I get? We add the complex the real parts together, and then you also add the imaginary parts together, and the imaginary parts have 2 and negative 3. You can say 3 minus 3. We are using the distributive rule, and that becomes 7 minus i. 7 minus i. Okay, so the b, similarly, when we do that, you can also have z2 minus z3, and that will be equals to z2 is 4 minus 3i. So we are subtracting z3 from that. That is minus 3i plus 5i. So minus 3, let me create the I here. Minus 3 plus 5i. Okay, so this one, 4 minus 3 minus 3, it gets, actually, yes, I'm write the answer right away. Gets 7 minus 3i minus 5i gets minus 8i. So that answer is this. So simple. Okay, so you can actually do more, find more examples, so it's very elementary. So the commutativity and associativity laws hold for addition of complex numbers, and that is when you have u and w are any complex numbers, then we can write u plus v equals to v plus u. And how do you call this one? Commutative. Okay, likewise I can also write u plus v, let's say, plus the third one w is the same as u plus v plus w, and this one, I call this one associative. So you can look out for the proofs. So simple, and you can prove them in your course material. Go through, you can see the proofs over there. So simple, elementary. Multiplication of complex numbers. Okay, the product of two complex numbers is defined so that the usual commutativity and then distributive laws hold. So here, let me guide you some more, and let's see how we are going to do that. So when I have from, let's say, z1 equals to a plus bi, and then z2 c plus di. So we want to find the product, keeping in mind that I squared equals -1. Don't forget about that. So z1 dot z2 is actually equal to, you are multiplying them together, that's a plus bi dot c plus di. Okay, so what do you get? You multiply them together, that is ac plus ADI plus BCI, and then the last one plus BDI square, I dot I square. Don't forget about your I square becomes negative, so I can get AC minus BD because I square here is -1. So AC minus BD, and then I can also simplify using the distributive law, the i's together, AD plus BCI, and that is the multiplication rule. Let's look at example for the next. Suppose that z1 equals this, z2 and z3 we want to find. So I'll do one, I'll leave the one for you as an assignment. So we want to do A, z1 dot z2 is 1 3 plus 2i dots, I've told you already, is the same as multiplication, minus 3i. So how do you multiply them together? So let's multiply them. 3 times 4 is 12 minus 6, 9i rather, that's 3 times minus 3i gets 9i, 2, 9i, right, is very well. 2i times 4, I get plus 8i. 2i times minus 3i. What do I get? Don't forget about your minus 1, so you get positive 6. That's -1 times -1. Okay. Or -1 times -6. So here, when you simplify it, 12 plus 6, I get 18. Minus 9i plus 8i gets minus I. And that's answer this question. So go ahead and do the other one. So simple. Let's take this note. Note that if I have, let's say, 5.z2 here, is so simple that if you want to multiply a real number by a complex number, it's so simple to go by. So that is 5 multiplied by 4, that is z2 for minus 3i. What do I get? 20 minus 15i. Okay, so you can do the rest and you find more example in your course material. So as with addition, the usual properties of commutativity and associativity hold for multiplication of complex numbers. So we did that in addition, so you do that also same in multiplication. So just an assignment, so go ahead and do. If you find difficult, check your course material, it is there. Division of complex numbers. So division of complex numbers is much like rationalizing the denominator of a rational expression. So here we have division on top here of complex numbers. Okay, so you should find solve for complex numbers, or to find the quotient. All that I have to do is that we multiply the numerator and denominator by the complex conjugate of the denominator, and that gives you the simplest how do you call it, solution. Okay, so for instance, I have ai, or let's say b first, a plus bi divided by c plus di. So if I want to find the conjugate pair, a plus bi divided by c plus di. So I want to find the quotient, rather, c minus di, or divided by c minus di, in that order. Let's look at examples in the next. Example 4, we want to express -1 plus 3i all on 2 plus 5i in the form a plus bi. So here I can write my -1 plus 3i, and write it very well, minus plus 3i, all divided by 2 plus 5i equals 2. minus 1 plus 3i divided by 2 plus 5i. You multiply both top and down by the conjugate pair, and the conjugate pair of which number? The denominator. So instead we say multiplication, you can also use dot. The dot is agreed or multiplication. So I'm using dot here, or you can also use multiplication. They are the same. If I write dots, like you can see clearly. Okay, so that's times 2 minus 5i, the conjugate of the denominator, 2 minus 5i. Now you simplify this. What do I get? You get 13 plus 11i, or divided by 29. Don't forget that your I will hold square root of -1, I equals to square root of -1. Don't forget that. So it's very, very necessary. In that instance, I can say that -1 equals to I square. So from here, you can just write in the form a plus bi. So I can say 13 on 29 plus 11 on 29 I, and that answers that. Okay, let's look at the next example. So here, don't forget about where your a equals to 13 on 29 and then your b equals to 11 on 29. Okay, the next example. Suppose that z equals to that, z1 is this, and z2 is z3. You want to calculate these two. Let me do one and then I'll leave one for you to do. So z1 on z2 equals to 3 plus 2i, or divided by 4 minus 3i. And what do? I multiply by the conjugate, 4 plus 3i, or divided by 4 plus 3i. Now you simplify this further, you get 6. Yeah, 6 plus, that's 17i. You multiply the down difference of 2 squares, 4 squared, that's 16, minus 3 squared, so you get 7. Okay, so and what do I get? And they're the same as 6 on 7 plus 17 on 7i. Okay, so go ahead and do the rest. So simple, like ABCD. Let's look at some properties of this complex numbers. We say that for any two complex numbers, z1 and z2, the conjugate of z1 plus z2 is equivalent to z1 conjugate and then plus z2 conjugate. Okay, similarly, when you find the conjugate of the product, is same as finding the conjugate of each of them and multiplying them together. So that is actually properties of the conjugate. And likewise, if you also have the division, you divide them before you find the conjugate. Is the same as the conjugate of each of them before you divide. So this sounds usual things we know already. So proof, this one, just look out for the proof, and then it's so simple, like ABCD in your course material. It's so simple. And then guess what will happen when the z1 is not z2 is not equal to 0. Rather, z2 is not equal to 0, because we actually want to avoid the denominator to be equal to 0. So here z2 is not equal to 0. Good. So in this session, we have established that complex numbers can be added, divided, or subtracted. The commutativity and associativity laws hold for both addition and multiplication of complex numbers. You also find the quotients of two complex numbers by multiplying both numerator and the denominator by the conjugate pair of the denominator. So this ends this session, and then we meet for the next session. Thank you for your time.